Very good morning to all. Welcome back to my course. This is Nagina Parveen, Associate Professor in the SR University. So today we will learn about the Butterworth filter designing steps. So firstly I will consider first low pass filter. So from the low pass filter to nth order, first order low pass filter I will consider. Thereby we will design about the nth order low pass filter. Then from there we will design the how to find out the order of the filter as well as the cutoff frequency equations. Now let's start. So in last class we have discussed about what is a filter, how many types of filters are there, how it is classified and all. Okay, so firstly if I consider RC circuit, the analog filter, then this analog filter will have a transfer function as h of s is equal to 1 by 1 plus s into RC. If I substitute h of s as j omega, then h of j omega will be, then the frequency characteristics is equal to 1 by 1 plus, as well as substitute the cutoff frequency as 1 by RC. If I substitute the values, then I will get this is a transfer function for first order low pass filter. So why I am considering first order? S power 1. Suppose if s power 2 s square, then this is a second order. If it is s power 10, this is a 10th order. Then if it is a nth order filter, then for nth order filter I can have, if I find out the magnitude, I have square root of 1 plus this real part whole square plus imaginary part whole square. If I take square on both sides, then this frequency response will be 1 by 1 plus omega by omega c whole power 2n. It is first order. If it is nth order, we have 2 power n. Now, so remember this, give it as equation number 1. So here omega is, so omega c is cutoff frequency and omega is c is a frequency. Now we have, if in the same equation expression, if I substitute omega as 0, if I substitute omega as 0, the maximum magnitude is, that is 1. So we have already seen about, so it has the maximum frequency response, frequency characteristics will have a gain of maximum 1. Now if I take these as in terms of dBs, then for dBs we can write as, so take as equation number 1 firstly. So this equation number 1 is whole square is equals to 1 by 1 plus omega by omega c whole power 2n. Now if I apply 10 log on both sides, 10 log on both sides in terms of for dBs, then I have 10 log of the magnitude of h of j omega whole square is equals to, so 10 log base 10, it is 1 by 1 plus omega by omega c whole power 2n. So whenever we have this 2 will goes to this, so multiply by 10, that is 20 log base 10, the magnitude of h of j omega. It means in terms of dBs if I have calculated, then I have 20 log of base 10, the magnitude of h of j omega is equals to 10 log 1, log 1 value is 0, minus 10 log the denominator value omega by omega c whole power 2n. Now log 1 value is 0, in this 10 log base 10, 1 plus omega by omega c. If I observe the same characteristics, so this characteristics is, it has a passband frequency, stop band frequency, passband attenuation and stop band attenuation. So this is 0, and x-axis is omega. So it may be sometimes it is equals to omega p, and the omega will be sometimes equal to omega s, stop band frequency, stop band, pass band edge frequency, stop band edge frequency. And suppose if it is, it have the pass band attenuation, that is alpha p, and at stop band edge frequency we have a stop band attenuation, then that is alpha s. Now remember, so this gain is 1 for omega is equal to 0. So when omega becomes omega p, we have a gain of alpha, that is passband attenuation as alpha p. At omega is equal to omega s, we have stop band attenuation of alpha s. Now log 1 value is 0. So I have the overall value is 20 log of base 10. The magnitude of mod of h of j omega is equal to minus 10 log of 1 plus omega by omega c whole power 2n. Now at omega is equal to omega p, then what is this 20 log base 10? This dBs is equals to the passband attenuation. Now if I substitute the same in terms of equation number 2, then I have alpha p is equals to 10 log base 10 1 plus omega by omega c whole power 2n. Now if I take this 10 to the left hand side, so I will have 0.1 alpha p. Again if I take this log to the left hand side, then I will have 10 power 0.1 alpha p, and this one also if I take it as minus 1 is equal to omega by omega c whole power 2n. So what is here omega? Omega is equal to omega p. So therefore omega p by omega c is equals to 10 power 0.1 alpha p minus 1. So give it as equation number 3. Then we have in the same way, if omega is equals to omega s, then 20 log dBs will be equals to the stop band attenuation. So for stop band attenuation, omega is equals to omega s. Then the same equation number 2 becomes alpha s is equals to 10 log base 10 1 plus omega s by omega c whole power 2n. Then again if I take this 10 to left hand side and this 10 power, so 10 power 0.1 alpha s, and this one also minus 1, then omega s by omega p whole power 2n. So give it as equation number 4. Now divide the equation number 4 with the equation number 3. Therefore you will get it as omega s by omega c whole power 2n divided by omega p by omega c whole power 2n is equals to 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1. Now here omega c and omega c can cancel. Now we have omega s by omega c whole power 2n is equals to 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1. Now I have to calculate the order of the filter. So what is the order of the filter? Right? So for this purpose I am taking again log on both sides. Apply logarithm on both sides. then 10 log of omega s by omega p whole power 2n is equals to 10 log 10 power 0.1 alpha s minus 1 by 10 power 0.1 stop band passband attenuation. Then this 2 I can write it down as 20 n log of omega s by omega p is 10 is equals to 10 log of 10 power 0.1 stop band attenuation divided by pass band attenuation minus 1. Now 10 here 20 here 10 will get cancelled. Therefore we have here it is 2n log of base 10 omega s by omega p is equals to log base 10 power 0.1 . Now to find out the order of the filter, take this to denominator and this, so we have log base 10, the numerator value divided by the denominator value, that is omega s by omega p. Then n value if I write, n is equals to 1 by 2 log 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 divided by log base 10, the denominator value. Now this 1 by 2 if I take it to the log to the internal side, so therefore the n value, the order of the filter using filter order, n we can find it as n is equals to log of base 10 square root of 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 divided by log of base 10 omega s by omega p. So this is a order of the filter we can consider, we can find using the given specifications. So in general we can consider it as it should be always either greater than or equals to. So where alpha s is nothing but the stop band attenuation, and alpha p is nothing but the pass band attenuation, and as well as this omega s is equal to stop band edge frequency and omega p is equals to pass band edge frequency. So from the characteristics, if we know these four characteristics, these four values, then we can easily determine the order of the filter. Now, so we have two different formulas to finding the order of the filter in terms of stop band attenuation, pass band attenuation, stop band edge frequency and pass band edge frequency. Suppose if I consider epsilon is equals to as square root of 10 power 0.1 alpha p minus 1 and lambda is equal to square root of 10 power 0.1 alpha s minus 1. If I substitute in the above equation, then one more formula for finding the n value as n is greater than or equals to log of base 10 lambda by epsilon divided by log of base 10 the stop band edge frequency to the passband edge frequency. Now if I take the gain value is equals to epsilon by lambda by epsilon, as well as transition parameter, if I take it as k is equals to omega p by omega s. So if I substitute in the same above equation, then I have the final formula as log of base 10 a divided by log of base 10 1 by k. So this is one more formula. So to find out the n value, we have three different formulas. So depending upon the given specification, we can use any one out of it. Now next, finding the cutoff frequency. From equation number 3 and equation number 4, because there we have a cutoff frequency formulas. Now if I take the equation number 3, so this is equation number 3, omega p by omega c whole power 2n is equals to so from equation number 3, omega p by omega c whole power 2n is equals to 10 power 0.1 alpha p minus 1. Now what I have to find out? I have to find out this cutoff frequency. So for finding the cutoff frequency, if I take, this is whole power 2n, if I take this power 2n to the right hand side, so I will get omega p by omega c is equals to 10 power 0.1 alpha p minus 1 whole power 2n becomes 1 by 2n when it is coming to right hand side. Then here I have a cutoff frequency. So cutoff frequency is equals to omega p by 10 power 0.1 alpha p minus 1 whole power 1 by 2n. Now we already know that 10 power 0.1 alpha p minus 1, we have considered it as epsilon. 10 power 0.1 alpha p minus 1 square root. So same formula I can write it down as omega c is equal to omega p by epsilon power 1 by n, because 1 by 2, this is 1 by 2, right? So this is the two formulas. Or if I take equation number 4, from equation number 4 I have, from equation number 4, omega s by omega c whole power 2n is equals to 10 power 0.1 alpha s minus 1. Now same, take this 2 power 2n to the right hand side. You will have omega s by omega c is equals to 10 power 0.1 stop band attenuation whole power 1 by 2n. Therefore omega c is equals to omega s by 10 power 0.1 alpha s minus 1 whole power 1 by 2n. Now if I consider, substitute the lambda value as square root of 10 power 0.1 alpha s minus 1, then the cutoff frequency is equal to omega s by lambda power 1 by n. So these are the two equations we will have to find out the order of the filter as well as the cutoff frequency. Now the designing steps. Designing of analog low pass Butterworth filter. Now in the designing of low pass Butterworth filter, we have first step is find the order of the filter using the formulas. So we have 3 formulas. We can find out any one of the formula to find out the order of the filter. Second step is rounding of the n value order of the filter to next highest integer. Then step number 3. So step number 3 is finding transfer function. So this is called it as normalized transfer function. For cutoff frequency is equals to 1 radians per second. So in general the cutoff frequency may not be equals to 1. But if you are considering the ideal condition, first we will design the transfer function for the ideal condition. Later on we will design a transfer function for unnormalized transfer function for cutoff frequency, obtained cutoff frequency using the above formula. Then we have h of s is nothing but 1 by polynomial, that is represented as d of s. So 1 by s minus s1, s minus s2 and so on, s minus sk. So where s1, s2, s3 up to so on sk are poles of the system, poles of the transfer function. Now what do you mean by poles of the system? Suppose if I have a transfer function that is 1 by s plus 1, then s power 1, the order of the filter is 1. If I equate the denominator part is equals to 0, then s is equal to minus 1, then minus 1 is my pole of the system. Now in terms of Laplace transformation, we have stability condition. If all the poles of the systems lies on the left hand plane, then we can call it as a stable system. And coming to unstable system, if any one pole of the system lies on the RHS plane, right hand side plane, then it is considered as unstable system. If any poles lies on the LHS, that is imaginary axis, then we can call it as marginally stable system. So whatever the filter we are designing, that should be always in stable condition. Suppose if I have one system, that is h of s is equal to 1 by s square plus 3s plus 2, then s power 2, that is the order of the system is 2. If I equate the entire denominator, that is polynomial, is equals to 0, then I will have s plus 1 into s plus 2. Therefore the poles of the systems are minus 1 is one pole and minus 2 is one more pole. Similarly, to find out these poles of the system, we have the h of s is equal to 1 by s minus s1 first pole, s minus second pole, s minus third pole and so on, s minus sk. To find out this sk, we have the formula as cutoff frequency multiplied by e power j into phi k, where this phase we can find out using the pi by 2 plus 90 degrees plus 2k minus 1 into pi by 2n, where what is n? N is order of the filter, and what is k? K is starting from 1, 2, 3 up to so on, ending with order of the filter. Suppose n is equal to 4, then k values will be k is equals to 1, 2, 3 and 4. Starting value is 1 and ending value will be ended with the order of the filter, that is 4. Now we have Now we have procedure to find out this S1. If I substitute k is equals to 1 in 5k, then I will get phi 1 is phi 1. If k is equal to 2, phi 2 I will get phi 3, phi 4 if n is equal to 4. Then if I substitute in sk value, I will get S1, S2, S3 and S4. So therefore I have to find out the polynomial as S minus obtained S1, S minus S2, S minus S3 and S minus S4. Now we have a Butterworth filter table for different n values. Now next step is finding the cutoff frequency. Finding the cutoff frequency. So in the above derivation we have already find out the cutoff frequency as omega p by 10 power 0.1 alpha p minus 1 whole power 2n, or we can use the stop band frequency divided by stop band attenuation. So we can use any one particular formula to find out the cutoff frequency. Now the last step is after finding the cutoff frequency, then fourth step is we have to find out transfer function for unnormalized frequency. So already we know omega c from the above formula. Then for designing of low pass filter, we have to substitute wherever we have in step number 3. In step number 3, wherever we have S has to be replaced by S by omega c. For low pass filter, if it is a high pass filter, reverse, S has to be replaced by cutoff frequency by S. So if it is a band pass filter, this last step will be differ depending upon the type of filter. Now for finding the unnormalized transfer function, HA of S is equal to, from use step number 3 as well as step number 4. From step number 3 we have H of S. From step number 4 we have a cutoff frequency, that is omega c. Wherever you have S in step number 3, replace it by S by omega c. So this is our analog, whatever obtain the transfer function. Now simplify after substituting. Simplify it. So therefore we got analog low pass filter designing through Butterworth. So these are the designing steps of low pass Butterworth filter. Now in next class we will discuss about how to design a low pass Butterworth filter using the given specifications. So we have discussed about how to, first I have considered about the low pass filter, first order low pass filter. Thereafter I have designed using a nth order filter transfer function. Then from the given specifications we have determined in terms of decibels, apply 10 log on both sides. Then we got some necessary equations. So later on we have substituted omega as first 0. If it is 0, the gain is maximum 1. If it is omega p, so we have considered it is as the characteristics in terms of dB as the passband attenuation. So we got the equation number 3. Next we have substituted again the passband, stopband edge frequency and stopband attenuation, and we have divided these two so that we can find out the order of the filter. So therefore we got the order of the filter as three different formulas. First formula is depending upon the passband attenuation, stopband attenuation and passband gain and passband frequency and stopband frequency. And there we have substituted for making the equation as simplification epsilon and omega, and there we got one more formula in terms of gain and the transition parameters. Also we have determined the n value. After that, cutoff frequency, equation 3 and equation 4 we have considered. That equations we have substituted to get the cutoff frequency. So this is the exact cutoff frequency we have for the given practical characteristics. Then the designing steps of low pass filter. So low pass filter, first using the given specification we have to find out what is the order of the filter, then rounding off to the next highest integer, then finding the transfer function for normalized frequency, then that is omega c is equal to 1 radians per second. Then depending upon the order of the filter we have those many poles, so poles can be determined using the formula. Then we have determined the unnormalized transfer function by substituting s in this two, using the step number 3 and step number 4. Wherever we have the omega c has to be substituted by s by omega, s has to be substituted by s by omega c. So if it is high pass filter, reverse omega c by s, so that we can obtain the unnormalized transfer function. That is our overall analog low pass filter designing using the Butterworth transformation, Butterworth approximation. Thank you so much.